Okay, so Neea is going to tell us about verifying complexity in Coq.
All right. Welcome everybody to this talk. I'm going to tell you about this kind of static program analysis, and then my plan to verify this in Coq. So I know a lot about my analysis. I don't know so much about formally verifying things. This will be my first effort, and I think it's a reverse situation for you in the audience. So I hope that we can converge in the middle and have this kind of fruitful discussion at the end. I will also say that this is part of my dissertation work for my PhD, so this is a very special topic for me. It's very dear. All right. So I want to start by giving you an idea of what kind of analysis I'm doing and what the kind of intuition is, how to use it. So imagine that I have this kind of a program here. This program is C. And then I have some input variables that the program receives, and then it will compute output variables, so those prime x1, x, and those are the output values of the program. So we're interested in input and output behavior. So I'm going to demonstrate to you this idea with a few examples. So let's say that my program is C, and it's going to perform the following computation. The question I want to ask is, how do the variables grow over this computation? Okay, there's nothing too complicated going on there. So if you look at kind of what the behavior there is, you can see that x1 has some dependency over x2, x3, and x2, x3 never change. So the conclusion we can draw here is that everything in this program is growing within a polynomial bound. Okay. The second example I'll show you is a little bit different. So I have a loop here now, and then I'm going to do some computation for x1. Okay. And I only have two variables here, so x1, x2. But if I now look at what is the behavior of my variables, I can see that, hey, I actually have exponential growth here for x1. So this would not pass my analysis. So the actual behavior I'm trying to look for is, how do I distinguish between these programs that have this kind of polynomial growth bound and these programs that do not? This is the question that I'm trying to tackle. So the good news is that I have a certain kind of technique that lets me do this. And what I plan to do is I want to formalize it, and I want to be able to say that, hey, I can, with this formal guarantee, give you this variable growth bound and establish this kind of correctness property for variable value growth. Okay. There is an existing analysis. This is called the MWB analysis, and it was introduced by Neil Jones and Lars Christensen in 2009. It's kind of, like I said, it's a static analysis, and what we're studying in this is the dependency between variable value growth, and what it's going to give us is kind of idea of the if the growth is within a polynomial bound. There are going to be different kind of dependencies that we're going to use to annotate programs that will give us this kind of answer, and there are, we use this kind of matrix to capture those dependencies. You can have a zero flow, which means your two variables do not have a dependency on each other. You could have an M flow, which is maximal of linear type. You could have a W, which is a weak polynomial, and you can have a P, which is a polynomial. So different kind of flows, and that's where we get the name of the analysis, the MWP. Okay, and then the idea is that as I'm looking at my program, I'm going to type each statement with this kind of vector, and then I'm going to collect those vectors in a matrix. And also, this is for this kind of deterministic imperative language. Is what I'm actually analyzing here. All right. So just to give you a feel for what this actually looks like, I'm going to give you another example. So I have here on the left, I have my program that I want to analyze, my simple imperative program. In the initial state, I'm going to have a matrix that's my identity matrix. It's size 3 by 3 because I have 3 variables. And then on the diagonal, I have the M flow. So this is what I'm always starting with when I'm running my analysis. So the first thing I have to look is I'm going to look at the if statement. I'm going to look at the true branch of that statement and see what's happening in there. I have a set of inference rules that I'm applying here that's telling me that if you see this kind of statement, you're going to update the matrix with the P flow at that position, and it comes from the rules that I have. We'll get there later. But that completes my analysis of the true branch. So the next thing I have to do is I have to go to the else branch. I'm going to reset my matrix to the identity, but the analysis for the else case is going to give me this PM in my matrix. And then to combine the if, I put those two results together. So it's a matrix addition, okay? That will finish the if statement, but I still have a while loop in there, so I have to go to the body of the while, and I have another rule that tells me if I see a while loop with this kind of, or if I just see a statement with assignment, I can do some W's in my matrix, but then I have to look at the while loop still. At that point, I compute the closure of my matrix, and I get my final result for this while loop. You want to note that I have here a side condition that there are some cases where I cannot apply my rules, but as I have my matrix now, it satisfies that rule, so I can keep going. And in the final step, I have to combine these two, so I'm doing this kind of composition of the two commands. And this is my final matrix. So I have successfully completed my derivation, and what this tells me is that all of my variables in this program has a polynomial growth bound, okay? And that's what it looks like. I want to note to you that in my analysis, I have some non-determinism. So when I'm doing my assignments, if you pay close attention, sometimes I put P, sometimes I put W, and you may be wondering where that's coming from. It's the fact that in my inference rules, I have 3 ways of how I can handle assignment whenever I see it in my program. So I was applying the E2 rule when I was doing the while loop analysis, but I could have equally chosen E3, E4. So there's some non-determinism here. So let's see if I went back to my step and I did the step 4 and I used a different rule. What's going to happen in that case is my analysis is going to fail because my side condition says that I cannot have a P anywhere in my matrix when I'm doing my while loop analysis. So there's some cases where the analysis can fail. Okay, so then the idea is that either you complete your derivation, which tells you you have a polynomial growth bound, or you fail, in which case you don't know where the program is at that point. And then the question is, for all the different choices that you could make at that non-deterministic choice, does there exist some way that I can complete my derivation? And that's what you're trying to find. Okay. At the end, you're going to get something called an MW bound, and this is essentially the matrix. The MWP bound tells you the different kind of relationship variables have on each other. I'm mentioning this because it will come up a lot in the proofs. So as this kind of custom expression that is created to express the result of the analysis. All right. So my actual more interesting thing why I want to talk to you about is my plan. As you've seen my technique, I want to prove this technique. And I want to prove it the way that it's defined in the paper. I have a plan of how I'm going to do it. So I need to define my programming language. So my simple imperative programming language. I need something to do my matrices. I need a type system. And then I need to actually finish my proofs. So I'm going to give you more details on this. So the programming language is easy. So I found that this is imp language with a loop. So I'm super happy about this because that was fairly easy. All right. I have a little bit of uncertainty whether I should study PLF because maybe there's something more that I need to know. I don't know. But that's that part. For my math part, I plan to use mathematical components. So I have looked at it already to see that it has some matrices and vectors. So I think that it's the right thing to do to use it. I also have, so in the proofs I use this MW bounds and honest polynomials. I think those can need to be defined, but they shouldn't be too difficult. For my typing system, I want to look at the FRAC book. And this is where I define my inference rules and connect my programming language and the matrix. So I will show you, this is my full set of rules. This is how I analyze my program. And this tells me how I type, which matrix goes with what statement and how to update the system. All right. And then the last part, once I have done all that, then I want to prove the actual theorems and lemmas that I have around this system to prove that it's a sound analysis. So the main result of the paper that introduces this method in the first place, the most important result is their soundness theorem. And what it tells you is that if I can finish my analysis, so the syntactic relation, then my program is derivable and there's a matrix that I can assign to it, then that means I have the polynomial growth bound on my variables. So that is the most important theorem in this paper, and that's what I want to prove. One thing that I foresee is possibly difficult is because the way these proofs were written in English, and they were not necessarily thinking in a constructivist sense. I have looked over them, but it may require quite a lot of rethinking of how to express them in a constructivist way. There are a bunch of other theorems and lemmas in there that they're mostly around, say like the loop rule or the if-else statement, and you have to prove the different inference rules. And then there are some quite difficult lemmas around that. So I have a motivational quote from the authors to say that these are sometimes very technical and non-trivial. And we'll see how that goes. We'll cross that bridge. Okay, so the main result I expect here is that what I want to do is, once I prove that this technique is sound, then I can say that, first of all, that it truly is a sound technique, but then I'm able to certify that if I get a certain complexity result from my analysis and say that it passes my analysis, then I know that this is true. And then it gives me this method that I could analyze programs in a way that I could obtain this result for programs in a program analysis way. All right. This is my timeline. I'm actively working on it. I've pretty much passed my programming language part, so I'm going to try to do the math and types next so I can get to my proofs. I have identified here also the resources that I'm doing. It's taken me quite a long time because just to do a step, I'm having to also study how to do it, and so this is adding quite a bit of time to it. All right. So I want to start a discussion with you. So you see my technique and you see what my plan is, and I'm really open to hearing what you think about it. Am I overlooking something? Should I know about something? But before we go there, so I've had a lot of discussions with people here at PUPL, and this last bit that I'm presenting is really inspired by my conversations here at PUPL, and it's more of a motivational thing of why do you want to do this? Okay, but before I get there, I'm going to tell you a few things that I've learned here. So earlier this week, I learned if you want to make a significant scientific contribution, you need 3 things. Okay, you need something novel, useful, and challenging. All right. So I have thought about this a lot. So I think I can check the box on novel because you may have not read the abstract, but in the abstract we discuss how much work there is on proving complexity. It's very little. And it's on different things. So I think the novelty box I can check. Challenge box, yes. Absolutely. All right. So what this leaves is the usefulness box. Okay, so then we're going into the motivations of this. I had a conversation with somebody that told me the following thing. He said, all right, I don't really think of Coq, I'm paraphrasing. I don't really think Coq is a vicious programming language. So if you take what you have is you're trying to implement something, and theoretically this is not too interesting. It's not like a lot of people can't use it. And if you look at it from the practical perspective of what you can actually analyze and get tight bounds with it, you can't. So it's not really useful. So you're kind of in the middle, and it's not really. So first thought was like, ouch. But okay, I thought about it more. And my second thought about this is I have heard, not necessarily in these words, but I have heard in different ways, takes on the kind of complexity analysis I'm doing. And I thought this would be a great chance for me to do a little educational moment about why you should care about existential bounds. So if we look at complexity analysis as a problem, this is a hard problem to solve. It's not well understood what the complexity properties of programs are and how do we analyze those things. It's generally a hard problem. Usually when we have submitted work to some place, there's this kind of idea of a metric and say, if I have a system that gets me tight bounds versus your system that gets existential bounds, then this system is automatically better. And I'm going to say that I don't think we should go that fast because there are various reasons and cases where you are concerned with the fact that there exists a bound of some kind. And I think that those two things need to coexist. And until we fully understand the complexity properties of the program, we should explore multiple paths. And it may not be the most significant, groundbreaking result, but it is a step in this direction. Say, let's see if we start formalizing complexity, what's going to happen. So I think that there are various reasons why this could work. Why are you going? Did hold on. All right. So there are various reasons why this thing could work, because I have this very nice system that works with the programming language. I have my inference rules. There are so many things that I look at Coq and I can say, hey, we could actually do this, which is not necessarily the same for the other systems. So I truly want to explore this path. All right. So I have had very nice comments also, so not just steps. I have, for instance, I have learned about people who have, in two different cases, have come to me that say, we're working on NP reductions, and we need to know if something is NP. And I said, haha, I know how. So that's one thing. And then another thing happened is when we submitted this abstract, we got this very nice email that was saying that, hey, there are some cryptographic applications we need to know complexity, and maybe if you can do this analysis and imperative progress, maybe we can have something like this in Coq. So these are just some ideas of how you can actually use it, and if we explore this path of what we can find and how it can be useful. All right. So one more thing. So I have worked a lot with this analysis itself. So we made a practical method. The way I showed it, that's not going to work for you if you try to make a static analyzer out of it. So we have made previously an extended method of this technique. So one idea of what you can do is, if you have the proof is of the flow system, and I have an extended method that is more practical, you could put those two things together. So that's one possibility. At the scope of where I'm at right now with my plan, I'm just trying to say that I can prove this technique, and that's it. I want to give you my email, because if you don't catch me, we're at the end of the conference. If you have some ideas or want to send me comments, that's fine. And then somebody left a very nice review for this abstract to say that's what an interesting proposal, and maybe we can have a nice discussion after. So that's it.
Yeah. Hi.
Hi.
I'm Christine from the University of Melbourne. So I have a couple of questions. So it looks like a cool proposal, and you were talking about practicality. So have you thought about whether you want to, like, maybe analyze the complexity of some examples once you're done? And also, have you thought about the class of functions that you can analyze? Something along these lines. Could be, I mean, or does the class have a nice name, or is it the class that happens to be analyzable by these matrices?
So that actually is more related to what we did with this analysis previously. So we did make a practical analyzer. So this is perfectly doable. It will take me much longer to get there in Coq, but yes. So it would ideally, I would like to be able to do that. Yes. So in software foundations, there are a bunch of examples where they have a parser. You could do this, and then analyze it in that way. Huh? Yes. So as far as it's the expressiveness of the class of programs that we can analyze. There's a comment from the original authors that came up with this method and say, we believe it's a powerful method, and they said we're going to write more. They didn't. But there is an intuition that this could be powerful. Potentially, there's some very nice properties about it. It doesn't require a lot of structure. So if you can map your programming language to it, you see it's a very simple syntax. It's the imp language syntax. Which is also a limitation, because if you're doing something with memory like allocation, then you can't. But for certain kinds of programs, you can use it. Yes.
I would like to take exception at one of the negative comments that you received.
Yes.
Which was about Coq is not good at analyzing programs. But this is not what you're trying to do.
Yes.
You're trying to prove an analyzer.
Yes.
It's not Coq that has to do the analysis.
Yes.
So you can discard this comment.
Yes. Yes, I
Well, I have to suffer censorship now, but I think that's not what you're doing. You said you have a working analyzer for some examples.
Yes.
So this is what you are proving, the analyzer.
I'm proving that technique, that if you get a positive result from the analysis, that you can say that this is truly true.
Yes.
Yes, the soundness of the analysis.
But this is at the same level of abstraction as CompCert with respect to validated translations.
Yes.
So this is front-running work of something that might be of the same scale as then working on a full programming language.
Yes, I have looked at Verasco. I find this very inspirational, what they did there. So it's behind you.
Hi.
Hi.
When you're doing the matrix representation of all the variable names, I was trying to figure out what's happening there with the matrices. Do you ever do matrix multiplication, or is it all sort of used only for matrix addition? No.
I'm trying to code it. Hold on, it's just one crazy.
Okay.
Hold on. I'll show you. Actually, I'll show you the rules. So if I'm composing my statements, I have to multiply.
Oh, okay. That makes sense.
Yeah. That's for any time that you compose something, you have to multiply. And then if you do the n star, which is the closer of the matrix, you have to multiply. So but in the very basic sense, what it is addition and multiplication of matrices. And We've had, in the past, we've added the constraint that you cannot declare variables in the program, because that way you know the size of your matrix as you start doing this analysis, and you don't have to worry about resizing. So it's very basic things, and I think that Math Comp is going to help me with that, I think.
Definitely.
Yeah.
What is the mathematical structure of the matrix element? MWP?
There's a, yes, it's a semi-ring with a plus and a multiply and WP and the infinity.
Okay.
Oh, sorry, infinity is in the other method. This one is just MWP.
You have a neutral element among them, or you have a specific multiplication table? Or in
Yes,
addition?
so anytime that you add, so m plus m is m, then if you get a p, then it's always a p, and p is the top element.
Hi, this is Byron from Chicago. Earlier you said that the analyzer can fail at times.
Yes.
Can you first of all give an example why, when that would happen? And second, what, if any, conclusion can people draw from a failed analysis?
Okay. So the idea is that you have your imperative program, and then you try to type each statement with a matrix. Because you have choice, going away, you have choice here. So if you have a variable expression, I can use my W, or I can use my P, where I put the P on the first vector, or I put the P on the second vector. So I have three choices of how can I look an assignment statement. For all the other rules, it's deterministic. But here I have a choice. So what can happen is if I have different kind of assignments in my program, some of those paths, derivation paths, they can fail, because if I have a loop and I have a side condition, see here, I can't have P's, and this says that I have to have on the diagonal only M's. So it may be the case that some choice of derivation path has led me to the point where I cannot no longer apply my rules. And they would always happen in the case of the loops. So that would be a case where the derivation fails, but that's not necessarily the case for the entire program. So you have to consider all the possible derivation paths. And if there exists one path that lets you complete the derivation, then you can say this is I can conclude that the variable bound is polynomial. But if you cannot find any, then it will fail for that program. So if you find one derivation, you know that the growth is polynomially bounded just by the existence of one example or one positive derivation path. If you don't, then you don't know where it is. And the reason, okay, I'm going to get to a little false. The reason we have this kind of choice is to allow to capture more programs in this system. So you want to be able to get as many programs as possible, but still have the guarantee of if I get a positive result, we know that the growth is bounded in P. And that's also the reason why we have the different kind of flows, like the M and the W and the P. That's a structure that lets you capture more programs. But it's not complete in a sense that you will miss some programs also, because it's not expressive enough to capture all the programs. Like you could make an example that has a P bound, and you could analyze it using this system, and it's not expressive enough to capture this. So we do have some examples of this we saw. Specifically, I cannot give you one right now, but I have seen it. So those programs do exist. Yeah.
All right, let's thank the speaker. We'll move on to the last talk.